Welcome students to 9.6, tangent planes and normal lines. What we're going to do today is we're going to proceed and continue with more applications on the parameterized curve, RFT. One of the things we're going to focus on today is what is the gradient actually. So let's focus on what's called the gradient. Remember, I did discuss the gradient before, but to understand it better, so we're going to go now in more details. Let's start with something called the level curve. What is the level curve? Let's consider the differentiable function z equal f of xy. We know very well that this is what? A surface. If you graph it, what do you get? You get a surface. So imagine that this is the surface that we have here, guys. This shape that any shape you can have. So let's suppose something like a boxy thing. So this is actually our surface. Let's take any point x naught, y naught on the xy plane, and let's sub it into this function, into our surface. So I'm going to replace x with some value and y with some value, like x naught, y naught. So when you plug x and y with some values, you're going to get a new value for z, isn't it? So this will give me a value. I'm going to call this value c. What's this c, by the way? We can call it, this is z sub naught. It's the result of substituting x naught, y naught into f of xy. Then what's going to happen here? This will take me to a new equation called f of xy. And instead of z, what do we call it? We call it c. So this is going to be a function in two variables, two-dimensional space. And we know that the graph of this function is nothing but a curve. And this curve will be called a level curve. So what's this level curve, by the way? The level curve f of xy equal to c is going to be a curve that is one of the curves on what? On the surface, like this one. Look at this one. This is what I'm talking about, this guy here. This one is what we call the level curve. Okay? This is one of the curves on the circle. You know, on Earth, we have the amplitude and whatever these lines that you see on the Earth, when you make the map, those are actually, each one is called a level curve. All right? So a level curve here is f of xy equal to c is a two-dimensional curve called a level curve. And this curve is graphed where? On the surface. And it has to be what? On the point x naught, y naught in the xy plane. So it's going to be a curve at what? Look what happens when I take x naught, put it here, and y naught, put it here. What am I going to get? I'm going to get z, c. And this is, we call it what? Z naught. So what's going to happen here? On the surface, there will be this curve here. How did I graph it? I graphed it by taking any point xy, like x naught, y naught, on the equation surface, and I got a curve. This curve, one of the points that is on the curve, remember when I put this one here, so I'm going to get x naught, y naught, and what? And z naught. So we know that, by the way, this curve also, f of xy equal to c, this curve is passing through the point x naught, y naught, z naught, because this is how I created this curve. Okay, so this curve was created by taking x naught, y naught into z equal f of xy. We get a c. This c is actually z naught. So that means I graphed, after graphing the curve, you have to know that the point x naught, y naught, and z naught must be on that curve. So this is what we call the level curve. So the level curve actually is a two-dimensional that we got it from what? From a three-dimensional. How do we get it? Just take any point in the xy plane, x naught, y naught, plug it in the z equal f of xy. This is going to result into a curve. This curve is exactly the red curve that you see on the surface. We know that this curve must pass through the point x naught, y naught, and z naught. To explain this one better, I'm going to take this example, guys. It says find the level curve of this function, f of xy equal to that. So what I'm going to do, I will call this function z, by the way. So z is equal to f of xy, and this is equal to x squared plus y squared. Let's call this one z. We all know how to graph this one. If you remember, we did this one before. Okay. So if you let x equal 0, what do we get? We get z equal y squared. So let's make the graph in 2 or 3-dimensional space. So I'm going to make the graph here. X-axis, y-axis, and z-axis. Z equal y squared, by the way, is going to be the red one now. Let's take that one. So this is z equal y squared. If we let y equal to 0 now, we get z equal x squared. So this is going to be like that. And here, probably like this. And then we make the graph. So what we have here is a paraboloid, as you all know. All right. Now, the graph of this one is what, guys? Is a surface. We got a surface. This is a solid surface. Now, on this surface, we're going to take the point 1 and 1, plug it in the function. So I'm going to find f of 1 and 1. What do we get? We get 1 square plus 1 square, which is equal to 2. Now, what do we have then in this case? So I'm going to take, so x squared plus y squared equal to 2 is my level curve. This is our level curve. What is this exactly, by the way? This is a circle of radius what? Square root of 2, right? So this one we know. This is a circle of radius square root of 2. So let's graph it here on the xy plane. So let's suppose this is square root of 2 on the y-axis, and this is minus square root of 2 on the y-axis, and here this is square root of 2 on the x-axis and negative square root. So I'm going to make the graph as follows. So what do we have? We have a circle of radius square root of 2 on the x-axis, but I don't want it to be there. Remember, here we know that x squared plus y squared equal to 2. This is the value of z. So now we know that f of 1 and 1 is equal to 2. But what's f of xy? It's equal to z. So this implies that z is equal to what? 2. When do we get z equal to 2? So we know, so the point 1, 1, and 2 is a point on the surface, is a point on the surface. Let's plug it, guys. x1 somehow here, and y1 is probably here. They will meet somehow at this point. So this is 1, 1 on the x-axis. Now we're going to go to z equal to 2. Let's suppose this is 1 and this is 2. We're going to go all the way to z equal to 2. Then go down and see where do they meet. They meet at this point. So what's this point now? This is 1, 1, and 2. This is a point on the surface, guys. All right, so now we have a point on the surface. Now what we're going to do, we are going to shift this curve up there. Sorry. Here is that one. I don't want this. We are going to make a curve that is actually passing through this point. So what did I do? I took this circle and I shifted up. See now? So now this is my curve. This is what we call the level curve. We said that the level curve is going to pass through the point what? Remember, we said it's going to pass through the point x naught, y naught, and z naught. I mentioned that at the end, our level curve, this is our level curve, is passing through the point x naught, y naught, z naught. We know x naught, y naught is 1 and 1, and we got z naught to be 2. So this is exactly our level curve, guys. It's this circle that is on this surface. This is our level curve. So you are on that surface. You are on the surface, and you are now walking on this curve, which is one of the curves on that surface, and it's called a level curve. And this is only when x is 1 and y is 1. And this led to what? Z equal to 2. So this is exactly what we have. That's it, guys. So this is the level curve for this function. All right. What if you have W is a function of 3 variables? So now we have something that can be graphed in 4-dimensional space, but we don't know how to graph anything on 4-dimensional space, right? Maximum we know is a 3-dimensional space. So from this one, I'm going to take any point, x naught, y naught, z naught, and plug it here, guys. X naught, y, replace it. So what do we get? We're going to get a value called c. When I plug it, when I know the point x, y, z, replace it with x naught, y naught, z naught, plug it in the function, we're going to get a value c. That means I'm going to replace this c here. So let's call it c, not k. Okay. So what's going to happen here? What do I have here? I have a surface. Okay. And this is what we call a level surface. In what? In 3-dimensional space. So if I have a function of 4 variables, okay, the level, we don't have a level curve now, it's going to be a level surface. So we're going to go 1 dimension down, and this will give me the level surface f of x, y, z equal to c. There. Let's look at this example. Oh, before we go to this example also. All right. What else do we know about this level surface? Let's suppose that you found the level surface, okay, of the function in 3-dimensional space, or the level curve. Let's suppose that you were in 3-dimensional space and you found the level curve to be f of xy equal to z naught, or c, okay, whatever it is. I'm going to represent my curve here, c, as r of t, guys. Okay. Then on this curve, I'm going to take this one, which is what? This is the vector that is tangent to this curve, isn't it? It's the vector that is tangent to the curve at this point. We call it r prime at t naught. Now, the gradient of the function at this point, we know the gradient from the previous section. What is this going to be? It's going to be this vector that is perpendicular to r prime. So the gradient is the vector that is perpendicular to the r prime, which is what? The vector that is tangent to the curve c, which means that this gradient is a vector that is perpendicular to what? To the surface, because this is a level surface, okay? This is a level curve on a surface. So the gradient now is going to be the vector that is perpendicular to the surface at this point. But this point now is going to be presented as what? X naught, y naught, and z naught. I will explain this one in this example, guys. Everything will be clear, I'm pretty sure, when you look at this example. Again, we have the same example. We have f of xy is equal x squared plus y squared. We know that this is the same thing as z equal what? X squared plus y squared. And we did it a minute ago and we graphed it. And what did we get? We get a paraboloid. So let's graph the paraboloid here. And this one goes up a little bit. And this one is down a little bit. And then we connect those with this curve. And this is the z-axis, the y-axis, and the x-axis. Now we have the paraboloid, guys. And in the back, x goes like that. And at the bottom, z goes like this. So this is 3-dimensional space. Now, let's find the level curve, guys. At the point 1, 1, I'm going to take f of 1 and 1. What's f of 1 of 1? We know it's a 2. So what do we have here? So the level curve is x squared plus y squared, which is f of xy, equal to c. What's c here? It's 2. And we said the graph is going to be circle of radius square root of 2, right? And then because z is equal to 2, so now but when x is 1 and y is 1, z is 2, the point was somewhere here. So this is 1 and this is 1, for example. Then we go to 2 on the z-axis. We went all the way up, then down, and we went up here, and we said this is the point, which is 1, 1, and 2. So now I have a point on the surface. At this point, what do we have? We have a level curve. What's the level curve here? It's exactly this level curve. Okay, so about that. So let me fix this one and erase this. We don't want that. So let's be more accurate. Okay, so now this is our level curve. All right. On the level curve, I have this point, which is 1, 1, and 1. Sorry, 1, 1, and 2. All right. What do we have here, guys? We're going to graph the gradient. Now, what's the gradient of the function? It's fx comma fy, isn't it? Which is 2x comma 2y. This is the gradient of the function. But I need to find the gradient of f at what point? 1 and 1. So what do we get? We get 2 and 2. If I replace x with 1 and y with 1, we get 2 and 2. Where is the point 2 and 2? If this is 1 on the x-axis and this is 2, so this is 2 on the y-axis, they will meet somehow here. So this is the point 2 and 2. So this is, guys, is our gradient. This is our gradient. But the gradient is supposed to be where? On the curve, on the surface. So this is now, guys, the gradient of f at 1 and 1. It's the vector that is perpendicular to the surface at what point? At this point. It's as simple as that. Got it, guys? So I have a surface. This one represents a surface. From the surface, what did we get? We got the red curve here. The one here is our level curve. On this level curve, how did I get it? I took x1 and y1, plug it in the function, I get 2. So I have x squared plus y squared equal to 2, which is a circle of 2, and I graph this circle down here. The circle is down here, but z is 2, so I have to carry this circle and go up to what? To 2. How do I do this? Simply, because z is 2 and x1 and y is 1, so we know this point, this one is a point on what? On the level curve on the surface. This is the point on the surface, and it has to be on the level curve. So what did I do? I plot this point, 1, 1, and 2, here it is. And on that point, I made my circle. And this is my level curve. Done. So then I found the gradient to be 2 and 2. I graph the gradient here on the x-axis 2, on the y-axis 2. They meet at this point. So this red one here is our gradient. But the gradient has to be perpendicular to what? To the surface on that level curve at this point. See, the gradient is at this point on the level curve, and it's perpendicular to the surface. That's it. And this is actually using the software with more intelligent, more sophisticated things. So this is how it goes. Also, if you have a function of, as I said, of 4 dimensions, so W is a function of X and Y, Z, so this is 4-dimensional. If you go one level down, if you plug the point x naught, y naught, z naught here, this will give you a C. This is called the level surface. The level surface here, we know that the gradient is going to be perpendicular to what? To any vector that is tangent to the surface. So the red one here is this one actually is r prime of t. We know that the gradient is perpendicular to it. That's it. Let's look at this one. Find the level surface of this one. Look at this. Now we're going to call this one W. So what do we have, guys? We have W is equal to F of X, Y, and Z. And this is equal to X squared plus Y squared plus Z squared. Now, he says, find the level surface that passed through the point 1, 1, 1. So the point now is 1, 1, and 1. I will plug it in the function. So W is equal to what? F of 1, 1, and 1. It's equal 1 square plus 1 square plus 1 square, which is a 3. So now W is 3. So what's the level surface, guys? What do we do? Take all of this. It's x squared plus y squared plus z squared equal to what? To 3. This is our level surface. And what is this, by the way? This is nothing but sphere of radius square root of 3. So I went from 4-dimensional space to a 3-dimensional space. When I went to the 3-dimensional space, what kind of surface did I get? I got a sphere of radius root 3. So let's graph it, guys. Here's the y-axis, here's the z-axis, and this one is the x-axis. So on the y-axis, we're going to go to root 3. And here on the left, negative root 3. On the x-axis, I will go to root 3. And in the back, we will go to negative root 3. On the z-axis also, I will go to root 3. And down here, we will go to negative root 3. Now, first, I'm going to graph this circle in the xy plane. Then I'm going to graph this circle between z and x. And come the one in the back. And finally, the one between x and y. So between z and y. And you go down here. Oops. Sometimes it's not easy to graph, accurately. So we're going to go like that. And then we go up. So what we have, guys, we have a sphere, as you see here. If you like to look at the back side of it. So if we remove this one, I will make it look like really a good circle here. So this one goes like that. And in the back, you can make it like this. So now this is the backyard. So this is a sphere of radius square root of 3, guys. So this is what we call the level surface. Now, what do we do? Find the gradient at the point 1, 1, 1. So let's look at the point 1, 1, 1, guys. 1, 1, and 1 on the surface. Where is 1? This is root 3. So I think this is 1, and this is 1 on the y-axis. They will meet here. So this is 1 and 1. Now from here, I'm going to go to z equal to 1 up there. Then go down parallel to this one and go all the way up. So this is the point here, 1, 1, and 1. Now I have a point on the surface, 1, 1, and 1. Let's find the gradient of f of x, y, and z. What is the gradient here now, guys? It's fx, comma, fy, and fz, because now we are in 3-dimensional. What's fx? It's 2x. What's fy? It's 2y. What's fz? It's 2z, the partial derivatives. So the gradient of f at 1, 1, and 1, which is he's asking for, find the gradient at this point, is going to be what? 2, 2, and 2. Where is this point 2, 2, and 2? So I'm going to take any other color like the green one. Let's suppose this is 2 in the x-axis and this is 2 in the y-axis. They will meet somehow in here. So this is 2 and 2. Now what I'm going to do is I'm going to go up to 2 on the z-axis. All right. And then come down to meet this point. So here's the point, 2, 2, and 2. And this one, by the way, represents the gradient. So where's the gradient? It's going to go from the origin to that one. So the gradient is going to go from here all the way to here. This is our gradient. But I don't want to start from the origin. The gradient has to be where? On that point. So what do? Now I'm going to make another one parallel to this one. And sorry. Let me remove those. Actually, I don't, those messy ones. Okay. All right. So let's do this with different color, as I mentioned. So I'm going to take the blue one. So I am going to take a vector that is parallel to this, and this is the gradient of f. This is the vector that is perpendicular to the surface, okay, and at the point 1, 1, 1. That's it. Imagine like this is a bowl and inside there is a light, okay, and then you make a hole. What's going to happen? A ray is going to come out, and this is your gradient. The sun itself, every ray that reaches to ground, if you look at the sun, anything hits your eye is a ray. This ray, by the way, is perpendicular to the surface of the sun at some point. And this is what the gradient are. So the gradients are the waves that are coming from the sun, as a good example. This is the graph of the function, by the way. All right, the last thing in this section is, let's suppose I have a level surface like this one. So now this one is level surface, not level curve, but the level surface. And let's suppose, guys, that we know the gradient. The blue one here is the gradient, which is what? Perpendicular to the level surface. Okay, let's take now any plane. You see, this is our plane now. Do you see that color here is a plane? This plane is tangent to the surface. At what point? At point x naught, y naught, and z naught. Okay. Let's take any other point. Here it is, x, y, z on the plane, guys, on the plane. And I'm going to connect it with this red arrow. You see that this arrow? It's the arrow that goes from this point to this point. And this arrow is r minus r naught. So which is p minus p naught. So it's going to be what? X minus x naught, I, y minus y naught, j, and z minus z naught, k, right? So I'm going to write it as a vector that goes at the origin. So this is how we present a vector that is hanging in the space. Remember, we subtract the endpoint from the big endpoint, and this is our red one. So this is exactly the red arrow. Now, what do we know? We know that the gradient is perpendicular to what? To the surface. So it must be perpendicular to what? To the plane at that point, isn't it? Which means it is also perpendicular to what? To this vector that is on the plane, which means because they are perpendicular, then I know that if I took the gradient at this point, if I took the gradient and I multiplied that product with this vector, by the way, is r minus r naught, what do we get? We should get 0. But what's R minus R naught? Look at this. This is R minus R naught, this one. And where is the gradient? Here is the gradient. Let's do that product, guys. What do we multiply? We multiply this by that. Here it is. Plus, what do we multiply? This by that. Here it is. Right? This is a dot product. Plus the last one times this. And this is the last part is equal to 0. Simplify this one. This will give you the scalar equation of the plane. You know what's the scalar equation of a plane? It's ax plus by plus cz equal to d. Remember that? This is the scalar equation of the plane. Remember from linear algebra. Or sometimes we call it n1x plus n2y plus n3z equal to d. Remember those things? I'm not sure. You know what's this n? Where n here is the vector that is perpendicular to the what? To the plane. I don't know if you remember this from linear algebra. So now we're going to get the equation of that plane. Here's an example. Find the equation of the tangent plane to the graph of this, guys. So I have x squared minus 4y squared plus z squared equal to 16. Now, don't forget that f of x, y, z, okay, if you move 16 to the other side, so what do I get? I get x squared minus 4y squared plus z squared minus 16 is equal to what? 0. So now I'm going to take all of this to be my capital F of x, y, and z, which is what? The level curve, okay? So, or in other words, let me explain it to you the way I mentioned it before. So if this is confusing, let me show you something. Okay. All right, guys. So remember that if I take this to be f of x, y, and z, don't we have 3 variables? Yeah, this is f of x, y, z equal to what? It's equal to 16, isn't it? Okay. Now, let's take f of course, this is supposed to be small f, not big f. Okay. Because I'm trying here to find the level curve. So here is f of xy equal to 16. So let's take the point f at what? 2, 1, 4. What's f of 2, 1, and 4, by the way? So let me fix another thing here. Now let f of x, y, z, let f of x, y, z to be x squared minus 4y squared plus z squared. Now, what happens if I plug this point in this function? What do we get? We get 2 squared, which is 4, minus 4 times 1 squared, plus z is what? 4, so this is 16. 4 minus 4 is gone. What did we get? 16, and this is exactly the right-hand side. So now we're going to say that f of x, y, z equal to x squared minus 4y squared plus z squared, okay, equal to 16 is our level surface. And now actually I can just remove this. So what's our level surface? This is our level surface, guys. Right? This is our level surface. What do we do with the level surface? I called it f of x, y, z equal to that. Now, to find the gradient, find the equation of the tangent plane. What's the equation of the tangent plane? The equation says what? It's f x at 2, 1, 4 times x minus x naught. What's x naught here? 2 plus the partial derivative of this one at 2, 1, and 4 times y minus y naught, which is 1, plus fz of 2, 1, 4 times z minus z naught. All of this must be equal to what? To 0. Alrighty, so this is what we have. What's fxy, by the way? What's fx, by the way? If this is your f, what's fx? We know it's 2x only. So this implies that fx at 2, 1, and 4 is equal to what? Put x equal to 2 here, you get 2 times 2, and this is the only thing we have, and this is equal to 4. Let's find the partial derivative with respect to y. With respect to y, guys, I think is minus 8x, minus 8y, sorry. You differentiate that, you get minus 4y, and the rest are zeros. So fy at 2, 1, and 4 is negative 8 times y, which is 1, and this is negative 8. Fz is equal to, the derivative with respect to z is 2z. So that means what? Fz at 2, 1, and 4. I'm going to replace z with 4. We get 8. So what do we have, guys? Let's go back here. So this is what? This is 4. We got this one to be negative 8, and we got this one to be 8. So what do we have? We have 4 times x minus 2 minus 8 times y minus 1 plus 8 times z minus 4 here, not z, not 4 is equal to 0. So let's remove that 4 here. Simplify this. So we have 4x minus 8 minus 8y plus 8 plus 8z minus 32 is equal to 0. So what do we have here, guys? So we have 4x minus 8y, then plus 8z is equal to what? Now minus 32, now minus 8 plus 8 is gone, so is equal to what? To 32. But we know this is all divisible by 4, so what do we have? So we have x minus 2y plus 2z is equal to 8. This is the scalar equation of the plane. So I consider that this is my f of x, y, z. I took it, and then I differentiate with respect to x, y, z, plug the point in it, and put it in the equation, and I got the value. Find the vector and parametric equations of the normal line to the tangent plane at this point. So we're going to go back to the same example. I had a surface, okay? I'm not going to graph the surface here, but in this one, we got that this is the equation of the plane, okay? He wants to find the equation, the vector equation of what? Of the vector that is perpendicular to the surface. Here's the question. He says, find the vector and parametric equations of the normal line to the tangent plane. Our tangent plane that we got was 2x. Let me check it, copy it down. So x minus 2y plus 2z. X minus 2y plus 2z is equal to 8. That was the equation of the plane, right? This is equation of the plane. All right. What's the vector equation of that one? We know that this plane is perpendicular to what? To the gradient, right? We know that plane is perpendicular to what? To the gradient of f at what point? 2, 1, and what? And 4. It's perpendicular. At what point? At the point 2, 1, and 4. At this point, I have a plane. Here's the plane. I found the equation of the plane. there's a point here which is 2, 1, and 4. We know that this plane is passing through this point, is tangent to the surface. I don't know what the surface look like, but it's tangent at this point. And at this point, what do we have, guys? We have the gradient of f. We know that the gradient of is perpendicular to that plane, isn't it? Okay. So how can I find the equation, the vector equation of that normal line? So here there is a line. I don't know what is it. So let's call, I'm going to change the color here. There is a line, guys, here, the red one. This line goes up and down, pass through this point here, and this line is perpendicular to the plane. At what point? At 2, 1, and 4, right? Now, what's the equation of this one? Remember, what's the vector equation of a line? X equal P, the point, remember that, plus T A, point plus TA or TD. Okay, what's the point here? The point is 2, 1, and 4. I know that this line is passed through the point 2, 1, and 4. Plus T, what's A? Any vector what? Parallel to the line. We know that the vector that is parallel to the line what? Is the gradient of F. What's the gradient of F? If you go back to the gradient, remember this give me what? So the gradient of F at the point 2, 1, and 4, we know what's this, remember? It's Fx, Fy, and Fz. And we got 4, -8, and 8. So this is the gradient. So I'm going to go here. So 8, -8, and 4. This is exactly the vector equation of the line, because the line is passing through this point. He wants it at this point. Because it's passing this point and it's perpendicular to the plane, then most likely it's parallel to what? Parallel to the gradient of F. Because the gradient is also perpendicular to the plane at this point. So I used it as my parallel line vector with a point on the line. I get this one. So this is the vector equation of the line. What are the parametric equations of the line? What do we do now? So X can be written as what? So X can be written as X, Y, and Z equal to 2 plus, if I multiply here, 8t, comma, 1 minus 8t, and 4 plus 4t, which means that X is equal to 2 plus 8t, Y is equal 1 minus 8t, and Z is equal to 4 plus 4t. Those are, by the way, the parametric equations of the line. Let's look at this one. Find the equation of the tangent plane of this one. So what I'm going to do, right, I need to get a function of X, Y, and Z, guys. So I have Z is equal to 25 minus X squared minus Y squared. I will move everything to one side. So what do we have if you move everything? So move this Z to the other side. So what do we have? So we have 25 minus X squared minus Y squared minus Z. I'm going to move Z to this side. What do we get, guys? We get 0. This is now what? This is our level surface. You know why? Because if you put 3 minus 1 here, so look at this, 2, 25 minus 3 square is 9, minus 4 square is 16, minus Z is 0. What do we get here? This one plus is minus 25, plus 25 is what? Is 0, so it satisfies the right-hand side. So this is our level surface. So from our level surface, we know that F of X, Y, and Z in this case is what? It's 25 minus x squared minus y squared minus z. This is the function of three variables. Now we are talking about what? A function in three-dimensional space. All right, now let's find the gradient of f. What's the gradient of f? It's fx, fy, and fz. What's fx, guys? The derivative of x squared is this is minus 2x. The derivative of this one with respect to y is minus 2y. The derivative of this with respect to z, I think, is -1. So this is our gradient. I need the gradient of f at what point? At 3, -4, and 0. So what do we get, guys? This is going to be -6, right? Because if I put 3 here, I would get -6. Put y 4, what do you get? -4, what do you get? You get 8. And z is fixed at -1. So this is the gradient of f. What's the equation now? So by the way, so this tells me that fx at 3, -4, and 0 is what? Is -6. Fy at 3, -4, and 0 is 8. And fz of 3, -4, and 0 is -1. Now we can find the equation. What's the equation of the line? Remember, it's fx at 3, -4, 0 multiplied by x minus x naught here, which is the 3, plus fy of 3, -4, and 0 times y minus this, so it's going to be y plus 4 plus fz of 3, -4, and 0 times z minus z naught, which is 0. All of that is equal to 0. But we already have this value, which is -6. So -6 times x minus 3. And this is fy is 8. So plus 8 times y plus 4. Fz is -1. So minus z minus 0 is equal to 0. Open this. So minus 6x plus 18 plus 8y plus 32 minus z is equal to 0. So I have minus 6x plus 8y minus z is equal to what? 32, and this one is 50. Move it to the other side, is going to be -50. This is, guys, the scalar equation of the plane. Probably you can divide by 2. You will get minus 3x plus, no, I'm not going to divide because z doesn't have anything in common. So I changed my mind. So this is the scalar equation of the plane. Now, can you find the equation of the line that is perpendicular to this plane? So now I have this plane, guys. There's a point here, which is what? 3, -4, and 0. At this point here, there is a line that is perpendicular to what? To the plane. I need the equation of the line. So I have a point on the line. Now, but we know that the gradient is perpendicular to the line. Here is the gradient of f, which was what, by the way? It was -6, 8, and -1, right? This is the gradient. So what's the equation of the line? Vector equation of the line perpendicular to the plane at the point, which point? 3, -4, and 0 is what? X equal to the point which is 3, -4, 0 plus t times the gradient, which is -6, 8, and -1. Why? Because the gradient is parallel to the line, which means that x is equal to 3 minus 6t. If I multiply that minus 6 times t, then comma, -4 plus 8t, and then 0 minus t. So the last one is minus t. But I can write this one as xyz. So that means x here is equal to 3 minus 6t, y is equal to minus 4 plus 8t, and z is equal to minus t. Those are the parametric equations of the line. And this is the vector equation of the line. This one is the vector equation of the line. Got it? So this is the vector equation of the line. That's it. So this will conclude everything about the gradient and how to graph the gradient and how is the gradient related to the surface, and how can I find the equation of the tangent plane on a surface. We see you guys on the next video. Okay, and we'll go after that to 9.7. Have a good day.